Hello, welcome everyone. We are just going to give it a few minutes so people can trickle in. But while we're waiting, if you want to pop in the chat where you're joining us from, we just love to see where everyone is from. So we will give it about 2 minutes and then we will get started. All right, it's looking like we've got really good representation from all over the US and then a few in Canada. So thank you so much for joining us. So just welcome to this Concussion Legacy Foundation webinar. We'll be detailing new research on CTE risk and prevention. It is so great to see so many of you tuning in from different places. Like I was saying, a lot of familiar faces, so welcome again. If we haven't met, my name is Dr. Samantha Bureau. I'm the Director of International Programs here at the Concussion Legacy Foundation, and we're excited to get started. So today we are honored to have Dr. Daneshvar here to present his remarkable new paper and the largest CTE study to date, which was released last week in Nature Communications. I'll also take a few minutes to detail the new CTE Prevention Protocol developed by CLF and the BU CTE Center that was inspired by Dr. Daneshvar's paper. We'll then leave time for a few questions at the end of the webinar, so please feel free to submit any you have to the Q&A box at the bottom of your screen, and we will get to those later. And then if you are joining us today because you or a loved one are suffering from suspected CTE symptoms, please know that you are not alone. We do have resources to help you manage your symptoms and connect you with peer support. So please reach out to our helpline. The URL is here on the screen, clfhelpline.org, and we'll also put the link in the chat for you. And then if you aren't able to stick around for the full webinar today, know that we're going to be sending out the recording via email, and we do post it on our social media pages. So if you aren't already following us, I would encourage you to follow us there. They're all on your screen. So now I'd like to introduce Dr. Daneshvar. So Dr. Daneshvar is the Chief of Brain Injury Medicine for Spaulding Rehabilitation at Mass General Brigham, an assistant professor at Harvard Medical School, and an advisor and friend of the foundation. So Dan, I will turn it over to you now to walk us through your paper.
Thank you very much. It's a pleasure to be here. And let me just jump over and share my screen. So we're really excited to be able to talk about this research. Thank you all for joining us today. It's really, I think, helped us advance our understanding of CTE and what we know about it. And you guys can see my screen, is that correct? Great. All right, so this is the paper that came out in Nature Communications last week. And the idea behind the paper is that we wanted to figure out what the relationship was between repeated hits to the head and CTE. Just to back up for a second, basically since 1928, we've known that getting hit in the head repetitively can cause problems later in life. It used to be called dementia pugilistica or being punch drunk. Later, it was in the 60s and 70s, it was referred to as CTE, as this disease, but it's the same process. What we didn't know, though, is what the specific characteristics of the hits to the head were that were responsible for problems later. You can imagine that it could be things like how many times you get hit in the head or how many concussions you have. That's largely what the thinking had been, like, especially 10 years ago. But specifically understanding what the components of the hits to the head were that led to problems like CTE later in life, that was kind of up in the air. You can imagine, though, that if we had a perfect experiment, something we might do is something where we were introducing repeated hits to the head in people at different ages and for different durations, and that we could modify some of the variables, like how hard they're getting hit, how frequently they're getting hit, the rate at which this is happening, the rotations involved. We could play with all these variables and then follow them throughout their lives and see who ended up with CTE and what factors were most closely related to the pathology and how severe it was. Now, that obviously would be incredibly unethical. But when you think about American football, you end up with a system that isn't too dissimilar from that model I just described, right? People start playing football at different ages. They play for different durations. Based on the levels they play and the positions they play, they're getting different frequencies of head impacts. They're getting different intensities of head impacts. They're getting different rotational forces associated with those head impacts. And we can then track all of these metrics and potentially get an idea of which of them are most closely related to CTE. And so that's generally what we did here. So there's a whole lot of reasons that we might want to model exposure. The main reason that we might want to do it is that it might let us identify different factors that are more associated with pathology, with clinical problems, with biomarkers. It also might help us improve our understanding of how the disease works. So these are reasons why we might want to do it. And our measures for how we modeled exposure before this study were more basic. We looked at things like the duration with which someone was exposed to repetitive head impacts. And so this happens to be from the new paper, but it's a similar analysis to what we did and reported in 2020 in Annals of Neurology. And so what you see here is a number of athletes that were included in this study. And on this axis here, it's the years of football played. And so you can see generally that the average length of football career in our study is somewhere around this 11, 12 years mark. But the interesting thing is when you take this exact same data, so it's the exact same participants, and as you see here, blue is no CTE, and as you get darker red, you get more severe stage CTE. So the exact same data is presented here in this right panel, except on this axis now, instead of just the number of people, it's for each given year, what percent of those people had no CTE versus stage 1, 2, 3, or 4 CTE. So when you look at the data in this panel on the right, what you see is it's pretty easy to tell without any advanced statistics that sure enough, as you go further to the right in this image, you're going to get more red and darker red, which is indicative of the fact that, as we found in that 2020 paper, the duration with which someone was exposed to repetitive head impacts through American football, that increased their risk of having CTE, and for those that had CTE, the severity of the CTE. And that's in fact what we also found in this paper as well. But beyond just looking at the duration of exposure, so how long someone played American football, we can look at exposure in a few different ways. And before I move on from this slide, I just want to point out, though, that we, in this cohort and really in any autopsy cohort, any study of looking at people's brains after they pass away, we're necessarily having a biased sample, right? We know that people are more likely to donate their brain for research, whether it be research in CTE or Alzheimer's or Parkinson's or any disease process. You're more likely to donate if you or your loved ones are concerned that there's a problem. And so people are necessarily enriched for symptoms in this cohort. And that's likely why, especially at this low end of range of years football played, what you're seeing here is these people, this is just everybody who played football in the brain bank. So a lot of these people, they might have been elite hockey players or boxers or had a military exposure or other exposures. So we can't make conclusions about, someone's risk of CTE based on these data. But what we can say is across all of them, when you look at football years of play is a very good predictor of likelihood of CTE and CTE severity. All right, but as I was saying, we were talking about how there's a lot of different ways that you could characterize exposure beyond just looking at years of play. So another thing that you could look at is, so this is years of play, durations, middle bucket here. We could also look at it based as an injury. So concussions are head impacts that result in symptoms. Those symptoms can be things like blurry vision, double vision, dizziness. Most commonly known, but not most common, is loss of consciousness. But that's not required for a concussion. Really, anytime you get hit in the head and you experience symptoms, no matter for how long, that could be evidence that there's a concussion. And so we can look at head impact exposure based on the injuries, based on whether or not a concussion occurred. We could look at them based on years of exposure, as I showed you. But we can also look at it biomechanically. We could look at it based on those other factors that we would ideally be able to look at. Things like how frequently the head impacts occurred, how strong they were from a linear direction, how strong they were from a rotational direction. These are other things that we can look at. And fortunately, American football provides us with an opportunity to look at it in that way because we have access to helmet sensor data. And so this is the head impact telemetry system that's been created by Simbex. And what this system does is it's a series of sensors embedded into a helmet that in real time allows the monitoring of athletes based on the number of impacts that they received with the helmet. Now, there's necessarily problems associated with these measurements, right? You can imagine that someone could get a hit to the head that might move the helmet in a different way than it's moving the head. Well, the sensor's in the helmet, and so it would potentially pick up an erroneous reading based on that. But it's pretty darn good. And those errors, they could go either way, either up or down. And there's no reason why there'd be some systematic error across all the subjects that are being reported in these studies. And so what we can do is aggregate all of them and average them so that those errors end up going back, being more or less adjusted for. And so that's in fact what we did. What we did is we took helmet sensor studies over almost 2 decades. There are millions of head impacts over tens of thousands of athletes that were studied. And these athletes were studied at the youth level, high school level, and collegiate level. And what we could do is we could figure out what the average, say, high school guard has in terms of the number of hits that they get to the head, the force of those hits, both linearly and rotationally, to come up with those biomechanical factors I showed you a couple slides ago. And we did that. So we ended up compiling over 30 studies. And what we created was what we're calling a positional exposure matrix. Now, this is something that's has a complicated name, but really is a simple idea, and it's often used in other kinds of studies, like occupational studies. Like, so for example, we wanted to figure out the relationship between an occupation that has asbestos exposure and mesothelioma. What you could do is create a similar type of matrix like this, where different types of occupations and their relative asbestos exposures are categorized, and then you could see how well those line up with, say, mesothelioma. Well, we did something similar here. We said for an average linebacker at the high school level, they get 460 hits per season. At the college level, they get 539 hits per season. If you look at the G-force, the average force associated with those linebackers hits in high school are 27.3, and in college is 22.3. Similarly for rotational acceleration. So what we could do is we could take these data and figure out for any individual what their risk of exposure is based on the positions they played and the levels they played at the youth, high school, and college level. Now, importantly here, you might notice that the youth level doesn't have any breakdown by position, and that's simply because there aren't any published studies looking at youth forces or hits based on helmet sensor data across these different positions. So we just have the average over all of the positions. But so what we could do, so for example, this is how we might use this. So I was a guard in youth football and a linebacker in high school football for 2 years each. So you could say for me, my 2 years of youth exposure means that I was at risk for potentially getting 206 times 2 or 412 hits to the head, just based on the fact that I played 2 years of youth football. And then my 2 years of high school football would be associated at the linebacker position, would be associated with 460 hits to the head times 2 years. So we're talking about a little less than 1,000 hits to the head. You could combine those two and you get around 1,350 hits to the head, 2 years of youth and 2 years of high school. Similarly, then you could figure out the total G-force that I might have been exposed to. So if each of the average G-force for the hits at the youth level are 20, is 20 times 200, well, that gets us to 4,000 G. Times the 2 years gives me 8,000 G. And you could do the same thing then for the high school sports. And so you can imagine then how we could take this and project it onto people who passed away, who played much longer than 20 years ago, and figure out their total risks of exposure based on the positions they played and the levels that they played at. Now, you also might notice, though, that there's no NFL data here. And that's because the NFL hasn't published any studies based on the helmet sensors that they're now putting in some of the athletes that they have. So what we did for the case of NFL play is we made an assumption, which isn't a great assumption, but it's an assumption nonetheless, that college approximates professional play. And so for each year of professional play, we use the college numbers. To put in context, when we look at these G-forces that range between 25 and 29 Gs based on the high school level, and between 20 and 31 Gs based in the college level, it's helpful to think about what these mean because it's kind of abstract. So these helmet sensors aren't picking up any hits or any force to the head that's below 10 G. And the idea there is that a lot of those hits are incidental things. They might be things like when you're running and the helmet's not fitting entirely correctly and there's jostling associated with it, or someone's chin strap might not be on, something along those lines. Those are basically not counted so that we can then look at what are actually substantive hits. And when we think about what these forces look like, it's helpful then to look at what comparison forces are. And so a 10G hit is something like what a fighter pilot experiences during a roll. A 30G hit is a car crash at 30 miles an hour. A 50G hit is a typical boxer's punch to the head. And an 80G is where an average concussion lies. But there's no threshold above which there's a concussion. So there are plenty of hits above 80, 90, 100 G where a concussion doesn't occur. And so this is a pretty small print slide, and I don't mean to belabor it, but I just wanted to kind of put this in the next couple slides here so that we can go back to them if there are questions. But this describes our cohort. And what was previously described is that this is the largest study of CTE to date. We had 631 brain donors in this study, and without their donation, their family's donation, we wouldn't be able to have figured out what we found in this study. And so the majority of these individuals had CTE, and about half of them played at the professional level, as you see on this slide. We had a whole host of different positions that were represented here, including one of the questions we often get is plenty of quarterbacks as well. Now, when we look at them pathologically, again, most of these guys, about 2/3 had CTE. But beyond that, we also found that there was some comorbid other neuropathologic diseases amongst these folks, right? Especially as we got to the severe CTE range, that, around 1 in 5 of these folks had other neurodegenerative diseases. And many of them, unfortunately, had dementia, especially when you got to the severe CTE range. 3/4 of them, of the people with severe CTE, had dementia, which is impairments in your thinking, memory, and ability to do things that are so significant that you're not able to take care of your bathing or dressing or grooming. It's a very severe disease for many of these people, unfortunately, once you got to severe CTE. And then what we found when we looked at those different possible factors is that concussions, so symptomatic hits to the head, they didn't matter at all in terms of our ability to predict CTE. However, duration of play, which we found in that previous study, still ended up being significantly associated with whether you got CTE, and if you got it, how severe it was. To the tune of every additional year played, increased your risk by about 15% of having CTE. But that isn't the interesting and unique part of the study. What the interesting thing was is that when we looked at things like the total number of hits that you got to the head, the total G-force, linear hits, acceleration associated with those hits to the head, and the rotational forces measured in radians per second squared, but the rotational force that people experienced in terms of their hits to the head, that all of those were also significantly associated with whether or not someone had CTE, and if they had it, how severe it was. But on top of that, when you looked at the total linear and rotational acceleration, so these two rows, they were better predictors of who had CTE and if they had it, how severe it was, than any of the other metrics. Better than the total number of hits, better than how long you played, better than concussion, although concussion wasn't significant at all. The other interesting thing here is when we looked at position, so these cumulative measures are based on helmet sensor data based on positions played. But position by itself, when you looked at the highest level that someone played, say professionally or in college, whatever their highest level was, you looked at their position also didn't predict whether or not they had CTE and didn't predict the CTE severity. Well, that actually kind of makes sense though, because if you think about my example, 2 years as guard, 2 years as a linebacker, what position was I? If you had to boil it down to one position, there isn't one position that describes my exposure. And we know that most of our football players, they didn't play one position their entire time. They bounced around multiple positions. And so the cumulative measures that we created, they help us account for someone's lifetime of experience much better than just one position does. And that's probably why position doesn't matter in these models, even though the number of hits and the G-force and the radians per second squared, which in part are based on position, they do matter a lot. And so this is another figure that is similar to the one I showed earlier, where we looked at, this is depicting the total force in the G-force based on whether or not someone had CTE, and if they had it, how severe it was, with more severe CTE getting this darker orange. And you can see that whereas that other figure had some more twists and turns associated with it, this one is a lot more clear. And that's why the statistics bear out what you see here with your eyes, that this is a better predictor of who has CTE and who doesn't, and how severe it is for the people who had it. And these are some more of the statistics then, just showing some of that relationship, where again, the higher this number is, this area under the curve, the better the model is at predicting who has CTE, and for those who have it, how severe it is. And so what you see here is total G-force and total rotational force. These two numbers are higher than duration of play or the number of hits alone. So now where does that leave us? That leaves us with in a really cool place, where we now have a better understanding of what it is that is potentially associated with CTE pathology. So what we can do now is use this information to potentially influence policy to help us potentially mitigate the risks associated with CTE and people's odds of developing CTE in advance. And for that, I'd like to turn it over to Dr. Bureau.
Thank you, Dr. Daneshvar. So as a reminder, we will be taking questions, but in the meantime, I will be presenting on the CTE protocols, which again, were inspired by the paper you just heard so much about. And that was a great segue, Dan, into the protocols. So again, if you could put your questions in the Q&A, we will get to them, but we will walk you through some of these protocols quickly. So this was a collaborative effort, by no means just CLF. We did collaborate with the BU CTE Center and some of our global authors that we've worked with in the past. So just to start, a really big thank you to all who helped out with this effort. But what we are looking at doing is taking the science that you just heard explained so well by Dan and look at how we can apply this in practice. So to start, let's look at a case study in American football. Again, this will be similar to what Dan was saying when he was giving his example of his career. But if we're looking at the average high school offensive lineman, they're averaging 734 head impacts this season. So here on this table to the side, we can see just a quick snapshot of maybe what those cumulative hits may look like across their career based on this data that we have. So if you were to, for example, reduce the number of hits, which you will hear in a moment is a component of this protocol, we'd be able to potentially reduce their odds of developing CTE, and in this case, by more than 50%. So looking at this table, we have the level of play along the one side, and we have, the year they were playing, the current number of hits they're taking, what a modified practice may do to the number of hits they're taking. And then in the green is the number I really want you to focus on, is the number of hits that potentially could be eliminated if we were to make modifications in practice. So in this case, across a career, you may see, just under 7,000 total hits taken by this player. Now, if we were to modify practice, and the reason we're looking at practice is because we do know most hits do occur in a practice setting. If we were to change how this was established, so we could cut the impacts in half per se, we could then reduce, just over 2,000 hits over the course of their career if they were to play just at the high school and college level. So looking at this from another angle to talk about the total forces, it's a very similar model, right? So we're looking at reducing the strength of the hits, and this could be done by eliminating, the hardest 10% of impacts a high school and college athlete may expect to take in a practice just by modifying the drills they could be taking. And across the table, if you look into the green, what we will see is a resulting, nearly 41,000 cumulative G-forces reduced by reducing the hardest 10% of impacts that these individuals are taking. So again, we're just looking at ways through this protocol, which I'll walk you through, on how to take the data we are getting from this paper and from the work that's been done with the accelerometers to try and find strategies to take this practically into, a practice in a game setting so that we can set our athletes up for success. Again, we cannot elicit change without education. So that is something else that is important to consider, that we do need to be educating our athletes, our coaches, our administrators, our governing bodies on CTE, and especially the difference between CTE and concussion, which Dan alluded to in his discussion. I think we'll get into that a bit in the Q&A, but really thinking about understanding this disease a bit better and what we can do to prevent it. The caveat is it is a little bit unclear right now when we should initiate this education. So that's something we need to continue to think about, so that we are educating people in a way that they can understand and that they can fully grasp. They have a good understanding of the long-term impacts they may be exposed to. So what this protocol really boils down to is a playbook for CTE prevention. So trying to really give those tangible tools that we can take to our organizations, to our schools, so that we can, have a better chance at reducing CTE. So the first way that we recommend doing this is by changing practice. So again, the majority of the hits are taken in a practice setting. So by changing practice, we can hopefully reduce the risk of developing CTE in a substantial way. So how can we do this? Coaches could consider to teach skills that don't include head impacts. So maybe there are drills we can do that don't include that, drills that result in fewer head impacts, or drills that result in head impacts with lesser force overall. So reducing the number of hits, we could maybe reduce the number of days that involved hitting. We could reduce the repetition of drills, maybe eliminating out of season contact. This is something that we're starting to see even at the professional level, where there are limits on the number of contact practices that can occur. Teaching tackling or blocking techniques that lower the rest of the head impact may be an option. So those are all ways to reduce the number of hits. We can also reduce the strength by, again, reducing repetition will, result in the head, greater impacts. Strength will reduce this metric. If we replace drills that are known to have, high impact hits with drills that are known to have lesser impact drills, just doing that swap could reduce the strength. And then again, teaching tackling or blocking techniques that lower the strength of the impacts to the head can again lower the risk. The next component that we recommend is changing games. And this is somewhere where there's a bit less control, right? So if we're looking at the practice scenario, there's a lot of control by the coach to change their practice how they see fit. When we get to a game scenario, there are a bit more moving pieces to make this happen, but nonetheless, changing games in a way that makes it safer overall for the long-term participation in the sport is something that should be considered. So this could include changing the rules. So if you were to reduce the number of hits and you wanted to change a rule, it could include in baseball banning collisions at home plate, for example, or in the NHL eliminating fighting. You could potentially reduce the total number of games. So placing the limit on number of games per season would reduce the number of hits, or potentially even shortening games to reduce the time spent in that scenario where hits could occur. If we wanted to look at this by reducing strength of hits, we could do so by, again, changing the rules. And in the NFL, an example would be reducing the number of kickoff returns by moving up the kickup line. One really good example in New York was in the Metropolitan Independent Football League. They eliminated kickoffs completely at the high school level as a way to reduce the force and strength of hits. And in soccer, we could potentially ban headers after punts and goal kicks, again, with this goal in mind. Or another option would be to increase the number and severity of penalties for hits to the head. So, examples could be, the NFL is now penalizing hits to the head and defenseless players. The NFL now also penalizes blindside blocks on punts. And then World Rugby introduced a head contact framework that increased the number and sanction for highest tackles that result in a hit to the head. So these are all examples of governing bodies that are implementing penalties as a way to assess this metric and make changes. Finally, the last way we are looking at reducing the risk is to change the age at which preventable repetitive head impacts are introduced. So really reducing that cumulative exposure by starting later. So by delaying the introduction of aspects of the sport that result in these head impacts, so for example, heading in soccer, it could then delay the exposure, reducing the number and severity of the cumulative exposure, which would be expected to reduce CTE risk. So for example, our Flag Football Under 14 campaign and our overall Stop Hitting Kids in the Head campaign is really advocating for delaying exposure to repetitive head impacts until age 14. We feel this is a reasonable goal. There are some governing bodies who are already making progress towards this. And the reason we think 14 is a great number is because the majority of athletes who play sports don't play beyond the high school level at an organized level. So that means that for most athletes, their exposure to repetitive head impacts could just be isolated to those 4 years of high school if you have them delayed until that level. So what does this look like? For example, USA Hockey and Hockey Canada have both delayed the introduction of body checking until age 13. So that is, a great way to reduce overall force and number of hits. The Football Association in the UK has delayed the introduction of heading in soccer, so football in Europe, until age 12. And then the CDC actually did a great case study where if youth tackle football players were to transition to flag football, for example, they'd be expected to go from a median of 378 hits per season to 8. So that's a huge difference in numbers. So that's another reason why we are huge advocates for flag football under the age of 14 here at CLF. So I don't want to spend too much time. The document does have a beautiful introduction, but Dan went over a lot of the science in that. But I do want to acknowledge the contributing authors and thank again everyone who contributed to the document. And if there's any questions about the protocol or you'd like to receive a copy, we are happy to send it to you. But with that, I would like to have the opportunity to invite Dan back so that we could do some Q&A. So I do see some great questions already in the Q&A. But to start us off, Dan, I would love for you to talk a bit more about the relationship between concussion as an injury and CTE. I think that's a common misconception we hear a lot. I've had so many concussions. What is my risk for CTE? So if you could get into that a bit, that'd be great.
Absolutely. Thank you very much for the great review of the prevention protocol. So the idea is that concussions can occur when someone's hit in the head and they experience symptoms. But you can get hit. So if I get hit in the head with a 100G impact and I get symptoms, then I had a concussion. But I can get hit in the exact same way in the exact same spot with another 100G impact and have no symptoms and no concussion occurred. And as you've shown, you can have, for each hit to the head that results in a concussion, based on how much sensory data, hundreds of hits to the head that are equal or stronger in magnitude, but that don't result in symptoms. And what this study suggests is that all those hits matter, right? It doesn't matter whether the hit results in symptoms or not. If you're hit in the head and it's a hard hit, it's probably causing some potential issues, especially as those hits accumulate to the hundreds or thousands over years and years of play. And so it's not just one or two or even four concussions that are causing CTE. It's all of those non-concussive hits in aggregate that increase your risk of CTE. And in fact, when we look at people who get one really bad brain injury, they don't get CTE. They get other problems, other pathologies. And I see many of them in my clinic. But those problems, it doesn't look like CTE.
No, that's a really great overview. And I think important for us to remember that, there's more to this discussion than simply just a concussion or post-concussion, persistent post-concussion symptoms. There's really a spectrum of things that can happen beyond a single injury versus working your way up to prolonged symptoms or potentially developing CTE due to, very high levels of exposure over a lifetime.
I don't want to discount also the serious importance of managing and treating concussions. And you alluded to this just now, with persistent post-concussion syndrome. Concussions can result in symptoms, and those symptoms can persist for weeks, months, even in some cases years. It's critically important to make sure that if a concussion happens, that whoever it is and whatever the mechanism is, that person's getting checked out and that they're not getting exposed to additional hits to the head, because the evidence suggests that those can cause much more significant issues.
No, that's very true. And I think, again, important to remember, and we had a question just come in that I think is relevant to what we're talking about now, and really asking, why do some head impacts that are higher G not cause concussion symptoms in some individuals?
Yeah, and so that's a great question. And the shortest answer is we don't really know for sure. The longer answer is that there's a couple different things that could be at play. It could be because, so the symptoms are necessarily issues with how the neuronal tissue, the neurons and the glia and the cells around it, how they're functioning. And it's possible there are plenty of regions of your brain that you're using, but that you're not aware of. And so they're doing important work, but it's not something that it's related to one of your senses. And so what we call those are salient regions of the brain, regions that are associated with sensation or other things that you're aware of. It's entirely possible those regions, the non-salient regions, are getting affected. And so there's an injury there. An injury would have caused symptoms if that was a region of the brain that was associated with things you can sense or feel. But because it's not, you can't tell. It's also possible that there's just a different process at play than what is causing concussion symptoms. There could be so concussion, our best understanding of it is it's related to this cell injury that results in firing of neurons in an unregulated manner. That's what's causing concussion symptoms. But there are other types of injuries that could occur that might not cause that, but that could eventually lead to CTE. So it could be a combination of one or both of those different reasons.
And what's great about the protocol is, by addressing total force and total impacts, you are inadvertently also addressing number of concussions, right? It's like we're addressing the overall exposure with the goal of preventing CTE, but kind of the collateral upside is also reducing the number of concussions and then hopefully the number of people with prolonged symptoms.
And that's a great point, because so much of what has existed in terms of concussion protocols have been targeted at the very important task of identifying who has a concussion, of training people to identify, manage, and treat concussions. But the horse has already left the barn at that point. The person's already gotten concussed. The beauty of CTE prevention protocols is that, as you said, they also prevent concussions. And so that's something else, that it's a dual benefit to these prevention protocols. We can target prevention and stop the hit before it happens.
Exactly. And I think that's really great for everyone on the call to remember, but also when you're thinking about, if you have children going into your sports season, thinking about having that discussion with the coach, the athletic trainer, so we can spread the message. But we do have a lot of questions here that are a bit more, nitty gritty about the data. So let's just jump in to that. But I guess the question we're seeing a bit recurring in different ways is, how can we interpret this data for non-football players? Is there a way to do that?
Yeah, that's a really great point. So your brain ultimately doesn't care what hits it, right? If you're getting hit in the head repetitively, you're likely at risk for developing CTE. And that's why we see CTE in a whole bunch of different people who have repetitive head impact exposure. So this data only looked at football players because we have more football players in the brain bank than we have for any other sport. In fact, every other sport combined. And so that gave us the ability to look at it at the football players in this way. Similarly, football players, unlike other sports like soccer or other sports, they have this characteristic nature to the head impacts that they're exposed to based on the positions and the levels they play, unlike, as I said, other sports. But that doesn't mean that these data are only applicable to football, right? The same principles that we've identified here for what increase the risk of CTE, they're likely at play no matter what the exposure is, whether it be from another contact sport, whether it be from military, whether it be from domestic violence. Any of these other things also likely have the same mechanisms underlying.
Yeah, and I think a sport that is coming up a lot lately in the media, just in general communications, is soccer, right? And heading the ball in soccer. So what kind of data do we have on soccer? What are we looking at in terms of trying to recreate this in a soccer population?
So there are helmets for soccer players, and but the sensors aren't too robust in them. There are mouth guard sensors that soccer players can use and have been published in some studies, but there's a lot of problems inherent to mouth guards that are not part of the same problems with helmets. Mouth guards, you can imagine, they move a lot more independently because people are chewing on them or moving them in and out of their mouth, or they might not be as well secured. And so that creates more error in the readings. And there just haven't been as many studies. There are 34 studies that were used in this for the creation of this positional exposure matrix, but there's only a handful in soccer players. So not only are there fewer cases of CTE in soccer players, there's also fewer sensor studies that are published. But what we do have, so we don't have these kind of data for soccer players, but what we do have are really good epidemiologic studies that show that soccer players are at significantly higher risk have significantly higher rates of dementia than non-soccer players. And that's been shown in multiple different studies across the world. And so that means that they're probably getting this head impact associated dementia caused by likely CTE. And so these same principles are underlie the mechanism for them likely as well.
That's great. And I will say we do have a very perceptive audience. So Victoria has a question as to why the G forces are generally lower for the college level than the high school level.
Yeah, that was something that was interesting, and it's something that's borne out in most of the helmet sensor studies. And so there are a couple different things that might be at play here. The first is that these G forces are the accelerations themselves, and force is mass times acceleration, right? So it's possible that the G forces aren't accounting for the fact that the college players are heavier, right? And so if they're heavier, even if the G forces of the acceleration is lower, their mass is higher, and so the overall force might be higher. That could be part of it. But the other part of it is, again, the fact that these guys are heavier, right? So if you're getting hit, that force is translating throughout the entire area that's been hit. So first, if I'm being hit and I'm bigger, well, there's going to be less acceleration for the same force. There's going to be less acceleration because there's going to be less movement. My body is going to absorb more of that hit. Second, if I have stronger neck musculature, well, or if I'm aware of the hit is coming because I'm a better athlete and I'm more attuned to what's going on around me, well, I might have a flexed neck. But either of those situations mean that instead of, if I have a loose neck, I get hit and my head is what's moving, the force is transmitted just to the mass of my head mostly. That's the much higher acceleration than if my neck is tensed and my entire body is moving. That's a higher effective mass, meaning that the force is the acceleration is the force is dissipated across more of the body, and there's less acceleration associated with it. So that might be one of the reasons as well. So there's a couple of reasons for it, but it is interesting.
Yeah, and it just really shows the complexity of trying to measure this and boil down what is impacting something versus not, right? There's so many variables to take into account, and every day we're just getting a little bit closer to kind of weeding out, I'd say, alternative options as opposed to being more certain about what may be controlling something. Digging into the data a bit more, just around the parameters, right? So what would you do for a person who played both ways? John's wondering, would you just, double it, adding both positions together? Like, how would you factor that into the analysis?
Yeah, so we had a lot of people who played both ways in our cohort. And what we did in these analyses for people who played multiple positions within a given season was a quick and dirty, we just averaged the two positions together in one. But that's not a great metric because we know people who are playing both ways, they're out there for more of the games. They might be practicing a little more intensely, so they might be exposed to more head impacts than someone who's not. And that actually might explain in part why so in general, a year is a year, hits are hits when it comes to exposure. So the G-force is the same, whether the G-force was experienced at someone at the youth level or someone in the professional level. But on top of that, we do see some differences between the G-forces, between CTE risk for those who played at the highest level versus those who played at the lower level. My guess for one of the reasons why that might be is that the people who went on to play in the NFL, the hits that they were exposed to in high school, well, they were the best athlete probably their town's ever seen, probably in the state. And so their coach, you better believe, was playing them every minute of every down, both ways, and special teams. And so that might in part account for why there's some difference, even though most of it is explained by G-force, but why there's some difference between the people who played at the highest level versus the lowest levels. It might just be that these modeling systems aren't accounting for the fact that these guys are playing both ways, for the fact these guys were taking more hits during the seasons than other people.
No, it's a really good point. And, thinking about, again, like these top players, you're right in the sense that the coaches will take every opportunity to put them on the field, right? So as you're going up through the professional levels, like these individuals not only have more exposure just from years, but just by purely being the best at what they could do at the younger levels, they're going to get more exposure. So how would you account for annual sports seasons? So obviously you think about something like football and generally a shorter season than some other sports. So what about, people are playing year-round soccer, year-round hockey? does this account for that? How can we account for maybe that framework as opposed to kind of a seasonal play?
Yeah, great question. So this model gives us some idea of what the factors that are responsible for CTE. And so if we can now apply this system, this knowledge that we've gained to questions like that. So for that question specifically, if these data are based on people who play a single season, and it's telling us the total G-force what matters. Well, so now if we encourage activities that like year-round play that involve more total G-force to the brain, well, these data suggest that that might increase your risk of CTE. And so we should be working towards limiting or mitigating those factors that result in more total G-force, like year-round play or multiple sports for a given athlete.
Makes a lot of sense. And I think just looking at time, I'll pick one more question. We do have a few more in here that I think we can either address via email or, the questions around protocols. Perhaps we do a webinar on our media project where we really dive in to the protocols, especially in football. But to round it out, you did show that head impact sensor setup, right? And how teams can use that to monitor. So is that something you encourage football teams to explore, monitoring their players?
I think the more data that we have about athletes in real time, the more we can make intelligent decisions about, who might be playing. For example, if we have helmet sensors and an entire team of athletes, and we see that Johnny is getting way more G's over a season than other athletes, we might pull Johnny and say, hey, what is he doing differently? And what can we potentially do to help mitigate those forces that he's experiencing? Is it a problem with how he's playing? Is it a problem with how he's hitting? Is it something we can address? That's really important and that's really useful. But on the flip side, these helmet sensors aren't free. And one of the issues that we have, when we're talking about at the elite level, we're talking about, athletes who have access to every resource available. But at the youth level, we struggle to get athletic trainers on the sidelines, let alone this kind of expensive equipment to protect the health of these athletes. And in fact, I'm going to quickly just share, I have this slide that I put together for a different presentation. So this is each of these stick figures represents 1,000 football players. And actually, sorry, this slide was prepared by one of my colleagues, Dr. Christine Bauer, University of Colorado. But each of these stick figures represents 1,000 football players. And if we then, let's see if I can change the slide though. I don't know why it's not. There we are. Okay. So there's about 4 million football players playing football every year in this country. But now, if we break that up and we look at who's playing at what level, we can see the vast majority of players are playing at the youth level. And these are the athletes who, it'd be great if they got helmet sensors in their helmets, but we can't even get athletic trainers for them. So yes, it's possible that in this cohort, we could get helmet sensors, but I'm more concerned about making sure we're helping everybody when it comes to safety.
No, it's a really great point. And looking at that diagram, I think it really brings us back to that discussion on flag, where it's like for that youth group, implementing flag football may be a bit more cost effective and potentially easier than paying for all those sensors for all those individuals to monitor the hits they are taking to try and reduce them.
Yeah, the fact that we're seeing CTE in so many NFL players, so many elite athletes, it's not because they're playing in the NFL. Their head impacts occurred. It's not only because they're playing in the NFL. Their head impacts occurred a lot at the youth level and the high school level and the college level and then at the pro level, right? So it's not, so if we could eliminate those head impacts at the youth level, then we're helping people throughout that entire chain.
No, that's a really great point to end on. And I do know in the chat, there was some interest on the veteran population and in the Q&A, and that is a population where I've been part of discussions where this is something that people are very interested in learning, right? And understanding the exposure of the veteran population and trying to implement similar tactics to explain that. We just don't have the data yet to perform this type of analyses based on their military service alone, but we do hope to learn. So thank you, Dan, again, for joining us. Really appreciate your time. I think, you know, your presentation was great. Your Q&A was just very insightful. So if anyone has other questions that pop up, please let us know. We're happy to answer them. Again, if you're involved in sports and are interested in implementing a CTE prevention protocol for your team, your organization, you know, in your district, please just send us an email at info@concussionfoundation.org, and we would love to help you out there. And finally, we are able to put on events like this for free through your support. So if you found this event helpful and want to pay it forward, donating $20 would help us continue to educate and create more resources for this community. And we are adding a donate link in the chat right now. But thank you for tuning in. Have a great rest of your evening, everyone. And please don't hesitate to reach out if you have any questions.
Thank you very much.